Good evening, mathematicians and lay math enthusiasts. My name is Jeff Cook, and this is Greg Volk and Dennis P. Allen. All right, we really had some hiccups since the first live stream. So we were streaming, but my mic was not streaming. So Dennis and Greg could hear me, but the live stream could not. Okay, so we have invited 10 mathematicians. I have invited 10 mathematicians. Each one of them could have could give very good feedback and are I don't know about experts in this field, but definitely PhDs who have interest in the Riemann hypothesis. And I only heard back from one. Some may join us. I heard back from one from Australia who said that he is interested in the research. He cannot make it today. And so we have not. And Greg, you sent it. You were saying earlier you sent some invites out to.
Yep. Yeah, I'm not sure if they even read it because nobody responded, so I don't know.
Okay, so good. Then what we were talking, if this happened, is that we're just going to go through it and continue where we left off before, and we're going to see, maybe some people in the YouTube will get some chats. So I have the chat here at YouTube. Let me just type something. You guys can see my chat at YouTube over to our left, right? Greg and Denny, you see this? I'm saying hello, welcome.
Yes.
All right.
No.
That's the YouTube chat.
Oh, I see it really small letters. Yeah.
All right.
Yeah, I can see the chat. It's small.
So that's YouTube. All right. So. All right. So there we go. That's YouTube is live. We are live at YouTube. All right. Good. So. All right. Jeffrey, thank you for setting it up. Let me see that phone there. Is it open there?
No.
Can you open it up so that I can just flip through there? Cool. All right. So what we'll do is we'll just continue with some questioning. I did want to show some things that I have learned about this AI really quick. All right. Let's see. I need to move this chat a little bit. All right. Okay. So after going through many conversations with the AI about this, you can see over on the left-hand side many discussions where I go over the same. I've gone over and over the proof and entered it a variety of different ways just to see if it always comes to the same conclusion, which it does, but it often comes to the same conclusion in a different way, and always was coming up to one little issue that I didn't understand it. Well, two things. There's a couple things I gotta go over really quick before we get into questions. All right. This is kind of a caveat with what the AI cannot do, and it states it right there on its homepage. It cannot give any information after 2021. So what that means is it has in its data that the Riemann hypothesis is a conjecture, and you can see this conversation I had with it. It can't change that. It's always going to consider a conjecture, even if it goes through and says the Riemann hypothesis has been proven. So it's always going to consider a conjecture. And the reason, finally, I got to the reason is because the mathematical community has to accept it before it's proven. It's considered proven. Okay. So what it says is that it's a rigorous proof. So I'm asking, isn't that a contradiction? If it's a rigorous proof, how could it still be a conjecture? And so it got over and over after going through conversation, it came to because of this issue with the mathematics community. And that makes sense. I think that's fair and reasonable. It has no authority to speak for the mathematics community, and therefore in its records, it's still conjecture. So let me get to the last. So I've done it multiple times and started over the thread. Let's see what we got here. Let me find the one. So in the last video, kind of we saw that it said that means the Riemann hypothesis is proven. And here's the latest one. When I did it, it ran through. It says, this looks like a rigorous proof of the Riemann hypothesis you have done a good job of using the lemmas as building blocks to reach the final conclusion. But then it says this little thing. It is worth noting that the Riemann hypothesis is still conjecture, meaning that it is not proven to be true or false. So I consider that a contradiction. It went on, and he's saying, no, that's not a contradiction. And eventually got to the point of why, and the reason is because it needs to be, accepted, yeah. And so when I finally got that wording in there, it made sense. And so then I kind of rephrased it and said yes. Okay, so here it's it did say it's rigorous proof, a couple things. All right, so that's where that is. The other thing that I do want to let everyone know before we go is that sometimes its math is wrong, which is, now we checked the math very thoroughly, and I think everyone's fine with the math. But for example, and I know that I'll go over the paper a little bit with a couple of updates, the short version only. And the math sometimes is wrong as far as integrals. So I asked for and infinite series too. I asked for a value, a couple values, and it was saying, no, they're complex arguments, it would take too long. And I said, well, can you do one? He said, sure, here's one. He gave me the one. I said, can I have another one? And then he gave me another one. And I went and checked, and all three were wrong, according to Wolfram Alpha. So the integrals, an infinite series values, let me see where I can find it. It's just this math in that way is wrong. It's just simply not calculating. And I asked, why is that? I knew it was wrong. I trust Wolfram Alpha, and also because we've already been over these equations, and it matched with derived 5 that Denny checked. So I know that the equations are correct. So we got that as an issue too. So this alone cannot be, reliable for checking a math proof. But what it is very good at is kind of, it's very good at logic and picking up assumptions and definitions as the data has been given to it. I think it would be worth filing a bug to them on a couple of these infinite series calculations. Here we go. Here are the values that's giving. And these were just simply not even close. So here I got this precision from Wolfram Alpha for the infinite series, and the integral with a little less precision, but they're still equal, you see. So this is comparing the values between the Abel-Plana continuation and the infinite series. So it gave this as an argument for the infinite series, very nice long high precision value, and then for the integral it gave it, and that matches it. But it came up with this, I think pi plus I10, it gave this value here, which is not anywhere close. So that's, that's not good. All right. So checking the calculations, I would say is optional at this point if we want to have it check math. Okay, because that's not.
Can I jump in, Jeff, and just say?
Please do. Yes.
Yeah, as I see it anyway, there are three possible ways that the proof could be wrong or incomplete. Number one, there's a calculation error, which I seriously doubt. I don't think that's a problem. And number two is there's some issues having to do with infinity that we haven't considered yet, and that's a potential place where there could be something that we missed, and I'll grant that. I don't think we have, but the third is hidden assumptions. Did we somehow assume something, in the proof that, wasn't, that is not, the result is dependent upon those assumptions. And in my mind, at least, that's the biggest area that we need to cover. So, and I really don't think we're going to find anything in the first area where there's a calculation error. We've gone over this so many times. I don't think that's going to happen. So that's my opinion. Anyway,
I agree.
And secondly, I'm just, I'm a little disappointed that we didn't have more people here today, but also, I guess I just like to put out an appeal. I know there were a couple thousand people that watched the video a couple weeks ago, and I know that we've had about 10,000 people read the paper. So it's obviously there's been a lot of eyes on it, and I understand probably the majority of those eyes are not, maybe especially wouldn't consider themselves experts in math. So I get that too. But and I also understand that Riemann hypothesis proofs are kind of a dime a dozen. So there's a lot of them out there. We're not the only ones. I understand that too. I think that this one's unique in that it's a direct proof, which we've talked about that a little bit. I know you've talked about it a lot, but let me just, if I can, put it in as succinct terms as I am able to. A direct proof is like a proof of construction is a form of a direct proof, which would be like, proving that that the two sides of a right triangle, or that a right triangle always satisfies a squared plus b squared equals c squared, where the c is the hypotenuse. And you prove it by constructing a triangle, and it could be any triangle, but it's not every triangle, because you don't construct every single conceivable triangle to prove it. You only need to prove it with the one case, and then show that because it's an arbitrary case, you're able to show that by actually constructing it. And that's kind of what we're doing here. It's not exactly, but it is a proof by construction, which is unique as far as I know. And I don't know all the proofs that are out there. There aren't a lot of proofs. There may not be any other proof by construction of the Riemann hypothesis, which is what this is. We constructed, or I really want to give the credit to you, Jeff, because you did most of the work. But what we constructed was this Riemann generator, this function, and used that in a way which is kind of like constructing a triangle. And use that to show that they have common roots, and therefore the roots of one are the roots of the other, and therefore if we can show that always has the real part 1/2, which we do that by looking at and I know I'm kind of rambling here, but we do that by showing that the part of the proof, one of the variables plus the conjugate of the other variable has got to equal 1, and therefore the parts, the real parts of both, have to be exactly 1/2. And that's essentially what this proof shows. The math is really not that complicated, but again, I still keep coming back to, is there something we missed, in the hypothesis or whatever? And that's the question we're asking. We're pleading with the mathematical community, someone who has some credibility and some time, and say, yeah, let's, we've done the work, and we've done the part that shows that this is proven. I agree with this, and maybe we can push it to somebody like Andrew Wiles, who's somebody like that, who has lots of credibility in this area, or some mathematical professors at well-known universities, so that we can push this forward. And
we have somebody in our Zoom call has joined us, Cyan.
Oh yeah,
So what are your invites, Greg? Yeah, okay.
Yeah, he's in England, so he's
welcome.
I don't know what time in the morning it is there. Let's see, it's 3 o'clock in the morning. Way to go!
Yeah.
Oh wow, you're hardcore.
He's either real early or real late. I don't know which. Probably real
early. Yeah, I thought I joined for at least a bit.
We're getting some echo here.
That's okay.
Oh really?
I can hear him a little bit though.
So you just woke up?
No, is it still an issue? I can rejoin.
It's an echo. It's not the clearest, But...
Yeah, we're getting a lot of echo. I'm getting.
All right, I'll come back.
All right. So, Cyan, just for those that just came in, and I know we've been going at this for a while now. We struggled at first because the proof that, or the information that we had provided a couple weeks ago, the AI seems to have forgotten. So we kind of started a whole new conversation, and it's tricky to get the AI to understand what you're trying to do. we're getting through the first lemma. We got 3 more to go, so it
Well,
could take a while.
I don't think we need to prove, do we, that this
But
converges?
I guess what I wanted to accomplish was not only get it to agree to the proof, but also ask it, what are the assumptions that we've made, and are these results independent of the assumptions? And basically that's it. Or is there something in infinity that we didn't take into account? 0 and infinity are tricky things, obviously.
Well, I think, all right, so what I have learned is that, this issue that it doesn't remember things, I logged out and it came back, it doesn't remember. I have the saved conversation. Anyone can go through and do the same thing.
Where is this? Can we publish this saved conversation in some way so people can see it?
Yes, I can save this. I can publish this one. I've done it multiple times. I could publish. One of them I did publish, up until the point where it says the Riemann hypothesis.
Okay, well, what does published mean? Where is it? Where is it?
ResearchGate.
Is what I guess I'm getting at.
It's on my. I have it on my ResearchGate.
The conversation with the AI is at ResearchGate.
Yeah.
Okay. Right with the paper. I guess
it's in that same. It's in the same area. I can go and put them all up.
Yeah.
Denny read over it one day. So it has all of the the text where you could see. I mean, you step by step.
Right.
And then they can see that I didn't change anything. So if we go to, I mean, I just don't think people think we're lying. I mean, here we have.
Okay. Well, we've been at this for a while, and it's going slow.
I put this. Yeah, it can be. I have put this up on ResearchGate. Okay, this is the one we were continuing before the other day. Okay, and so it went through each one of the steps. I went through all of the functions. I've gone through all of the functions many times. So I call f of s. I was kind of checking different things. Didn't even call it the zeta function here. So a lot of different conversations with it, but all of it, it always comes to the same thing. It always says that the Riemann hypothesis, it's a rigorous proof of the Riemann hypothesis every single time. I've done it many times. Somebody else really needs to spend the time.
Let's review there are 4 lemmas and 1 theorem.
Yeah.
Let's just say them in English, what they are, one more time. Could you do that?
Yes. Lemma 1 is that the Riemann oscillator is equal to the Riemann zeta function at t equals 0. So the Riemann oscillator is
this
right here. All right. So this is equation here. All right. So at t equals 0.
Back up to that.
And it has that property.
Hold on, Denny has a question. Go ahead. What's up, Denny?
Yeah, you went on by the one where you reason that one of the terms is s can only have zeros.
That's later on. That's later on. That's lemma 2. We're at lemma 1. So lemma 1 is Greg. What's the lemma 1? The Riemann oscillator.
Yeah,
the oscillator and the function itself have the same zeros at t equals 0.
All we're saying is the
equation 15.
All right, what'd you see, Denny? Help me through it. Where you wanted me to go?
15.
15? I didn't.
We're not that far along.
We haven't got to 15 yet. All right, we'll get to 15 in a little bit.
I want to see 27.
15. I see. Okay, so 15. All right, so here's this is all it is. It's just saying that the oscillator is equal to the Riemann zeta function at t equals 0. All right. So how do we prove it? We define the oscillator, and
wait. Back up a little bit.
Okay.
Back up to 15.
Yep, right there's 15.
Now, weren't you arguing that only the middle term on the right could have zeros?
Yes, but we didn't get to that point yet here. We're starting from the beginning.
Well, I know, but something's bothering me here.
Yeah.
Assuming the middle term is 0, how do you know that the zeta function is 0 at that point?
All right. So the only thing it states is that the only possible zero of the zeta function would be when the middle term equals 0.
Mm-hmm.
No, I don't see that because it's a sum, not a product.
All right. So but we went over it. Look, can this term equal
The
0?
first
Denny?
term can't.
Yeah, the first term can't vanish. All
Can
right.
the last term vanish?
Uh,
In one case, it can. What can it vanish?
yeah,
from?
one case only.
Yeah, but that wouldn't be
if
that wouldn't be a zero of the zeta function, correct?
Yeah. So, but if the middle term vanishes,
Yeah.
then
But the middle term doesn't vanish. Well,
the other two, some of the other two has to vanish.
Okay, so here's all right. We have to go to Lemma 1. Let's back up. Greg had a question, and then we'll talk about this. We'll get to Lemma 2 in a second. Okay?
we're just coming at
Because
you.
I don't want to skip Lemma 1. All right, let's go back to Lemma 1. We'll come back to that, Denny. And I know what you're
All right,
asking.
okay, sure.
But let's let Greg. All right, here. So Lemma 1 is that the oscillator is equal to the zeta function. Here is the proof. We just simply let t equal 0. This is how the oscillator cancels to the explicit form of upsilon, which we defined here. We defined from the decay rate of alpha, and then we put it in explicit form, and everything cancels except for the Riemann zeta function when you're doing it with the infinite series. And then we do it also, we can show the same thing happens when you do it using the integral form. Everything cancels except the Abel-Plana continuation of that series. So all it is just algebra at this point.
Mm-hmm.
Do you see that? So that t equals 0, everything cancels out. All the non-analytic components, all the complex conjugates, all that cancels out and just leaves this behind. And so this is something people can check. It's very straightforward. The AI did check it too. So you can plug all this in and it can check it all. So therefore, the proof of Lemma 1 it's solid. All it is saying is that this function of the oscillator, that as we define it, whenever t equals 0, it is going to be reduced to the zeta function. That's all we're saying.
Yep.
All right.
Yep.
Lemma 2 is
Yep.
at this form, which we have, which is equivalent to the oscillator at t equals 0, and it's our new representation of the zeta function. Only the second term can equal 0. Now, Denny, you had a question about this.
Mm-hmm. That was the issue.
Well, the
before.
first term can't vanish, and
Right.
the second term only vanishes at 0. But if the middle term vanishes, you should show that the other two terms vanish too, don't you?
Okay, so what the Lemma 3 gets to the two different conditions of the different types of zeros. There's two types of zeros. When the second term equals 0 and when the second term does not equal 0. Yes, there can be zeros when these two terms cancel the third. But we're just talking, at this point, just Lemma 2 is just really getting to this issue that this is the only term that's going to 0. It's super simple. And I think this is the only one that has zeros. It could be
That's
0.
the essence of Lemma 2.
Yeah, if s equals 0, but s equals 0 is not a 0 of the zeta function, so it can't equal 0. So the only possible zeros of the zeta function occur, the only term goes 0 is this one. Yes, there are two types. We're going to get to that. That's Lemma 3. So proof of Lemma 2, if it's not obvious anyway, we can just put it because the first term is the multiplicative inverse of s minus 1. The third term is also the same, except for when s is equal to 0, which is not a 0 in the zeta function. Lemma 2 is proven. That's a very simple one. Okay, Lemma 3 now is where you're going.
Lemma 2 is the simplest of the four.
Yeah. The Lemma 3 is that there are only two types of zeros and that these two types are mutually exclusive. The first type is when upsilon equals 0, and the second type is when upsilon does not equal 0. That's it. There's only two types. And we're going to prove that when upsilon equals 0, the only possible solution is real part of s equals 1/2, and when upsilon does not equal 0, real part of s equal 1/2 is not possible. So real part of s equal to 1/2 only can occur in type 1 and nothing.
This is important
Very
because
important, but it's
upsilon
very
equals
simple.
0 is the Riemann hypothesis.
What? No, upsilon not equal.
Upsilon of s equals 0 is real part equals 1/2. That's what we're trying to prove.
Oh, we will eventually will prove that there are only two type 1. Yes, the final statement is
Yes,
there
but
are
at this
only
point, we're not. We're just
No.
okay.
All right. No, we're at this point. We're just doing it here. Just the term equals 0. That's all we're tackling. So each one of these is very, very simple every step of the way. The next one is that how do we do it? Well, we take the expression. Where was it? Right here, 19, and we rearrange and solve for upsilon. Then we let zeta equal 0. That is the condition that is required for all the zeros of the zeta function. There's none that are missing. So if we rearrange, what equation was it? 15, and solve for upsilon, we're going to get this. Well, not this. We're going to get over here. Let's just do it. Let's do it. I should have put it in here. We're going to do it right now. Well, Wolfram Alpha do it. All right. And let's not deal with the function at this point. This is just algebra here. All right, and we're just going to call this z. And we just tell, I'm going to call this u because, all right, solve this for u. All right, what's time we got? I think this Zoom call will end, so we have to wrap it up. Okay, so now we have, this is...
They'll tell us to cut it out.
Yeah, we'll have to. All right, so for all of the regions, you know, real part of s equals 0. All of them are the same. There's only a single solution for all of them. I'm going to copy it. Let's see if it will reduce it to the same form that I have. Yes, that's it right there. Right there. Okay, that is the form we're looking at. Now, if z equals 0, it's going to, s minus 1 is going to vanish. It's going to give a -1. Let's just do it. All right. All right, when zeta function is 0. Does that look familiar to you? It should. It's right there. Okay? All right, so that's what we get when, for all the zeros of the zeta function, they're all in this little expression. All the zeros. Trivial, non-trivial, critical, non-critical, all of them are in here. It has to be. It is a required condition. So that's why we're solving for upsilon. Well, what does this mean? What term can go to 0 in the numerator? We can express this numerator in terms of the real part and imaginary part here, and this first factor here cannot equal 0. It is always going to be a complex number, so this leaves only this factor here. Set 2 times real part of s minus 1 equal to 0. Add 1 to both sides, divide by 2. We have real part of s equals 1/2. It is the only possible 0 when upsilon equals 0.
Yep.
Make sense? That is the type
Yep.
1. All right, because that is cannot be a real number. All right, that is type 1.
That's half the proof.
Yeah, that right there. Well, yeah, that's half it. Now we got to go back and prove that it's mutually exclusive, cannot be in the other one. So we're going to rearrange and solve for the real part of s given, what number is this? 20. Given 20, solve for the real part of s. And you get this nice little quadratic, which we had a certain professor whose name we won't mention, did give us this nice little, he pulled the 1/2 out of there. So we can just look at this. If this real part of s equals 1/2, and this is the type 2, is when upsilon is not equal to 0 and zeta function equals 0. All right, so this term has to go to 0 for real part of s equal to 1/2 to be possible. Can this go to 0? No.
Neither of those goes to 0.
No, this cannot be equal to 0. Therefore, it has no solutions. that make this possible, and therefore real part of S is not applicable. The full description here is because of right here. 25 has no solutions because both factors in the product are non-zero. First factor, I can't read with all these windows open, but you can read it in the paper. Therefore, arguments having real part 1/2 are not applicable to the type 2 solution, which is equation 23. And there's only one other type. It's type 1. It must be here. So that reverse implies that if the real part of S is 1/2 and the zeta function equals 0, then upsilon also is equal to 0, which is this right here. Okay? So that's pretty straightforward. 3. Any questions about lemma 3?
I think that's the guts of it right
That's
there.
algebra. There's nothing.
Because the
hidden.
rest, I know, but it's the guts. That's the most important step, because step 4 is lemma 4 is obvious where this is going.
Yeah.
But go ahead.
Yeah. So that, I mean, step 3, that is just algebra.
Step 3 is the absolutely, that is the essence of the
Lemma
whole
3.
thing.
Lemma.
Is
Yes,
right there.
exactly. Because there's only two
absolutely.
groups. There's 2 groups of zeros.
1 and 2 are pretty trivial. 4 is kind of trivial too, but 3 is really, that's the big deal.
Lemma 4 technically doesn't need to be there, but we do expect people will argue what a solution is. Can a relationship be a solution? Can a solution be a relationship? And if it's possible. Because it is easy to prove lemma 4, we just do it in that argument. All right, so we're going to create a function. We're going to define a different function, g of s. Of course, if you notice, that is upsilon of s equal to when the zeta function is 0. But we're going to come in, define it independently, and just show that it's a geometric series. If anyone wanted to know what upsilon of s when zeta function is 0. Okay, and we're going to then define 2 types of these. We're not even going to call them zeros at this point. We're not even going there. We're just going to say this is a point on the left-hand side of the critical line, and this g of s to the power, it looks like to the power, but s rho r is a 0 on the right-hand side of real part 1/2. All right? They have to be on opposite sides.
They're superscripts, not powers, just to be clear.
Sorry, I know. When I look at it, it looks like a power, but it's superscript. Sorry. You were correct. All right. You should take over. No. All right.
No, you're doing great.
I'm trying. I don't do well when I get tired, but here we go. All right. Guarantee that the 2 distances are equal from the critical line. We do this by setting the one on the left side of the critical line is defined as being equal to 1 minus the point on the right. All right. We're just saying it has to be there. Therefore, their distance from the critical line are equal. Got it? All right. And we also have to define that their imaginary parts are equal. So if anything's in the critical parts, and we replace real part on the right with 1 minus real part of s, you see, we got on the left-hand side of the equation g of SL, and on the right-hand side, the explicit form of, what equation is this? 30. This is what we get. Everything cancels out to minus g of s superscript L. So this means for this case, whenever this happens, where are we at? Whenever we have 2 points on the opposite side of the critical line, defined in this way, where their imaginary parts are equal, whenever that happens, g of SL is going to be equal to minus g of SL. Does that make sense, Greg?
G of SL has to be 0. Huh?
Does that make sense?
Yeah.
Okay, good.
Of course.
All right, so let's go ahead and reduce it. What does that reduce to?
I just, my thinking is that this whole, your step 4 is, I don't know. Maybe it's necessary to do all this. It just seems the results seem obvious to me.
I know, but there was that professor, and he's a,
Yeah, he said
no
you gotta
dummy.
okay.
He said this is the final result, that was solution, and I'm like, well, no, it's reducing back. I don't think it really needs to be in the proof, but I don't like to have conversations over definitions. You know what I mean? So let's just define it then. What are we defining? We're defining this. All right, so what this implies is it reduces the same thing we had in the type 1, 0, which implies real part of 1/2. All right. So if real part is 1/2 and upsilon is equals to 0, and then it can't be, it's undefined. If we ever would want to reapply it somewhere else. All right. So I think it's straightforward, right? We all agree?
Mm-hmm.
Yeah.
Then it's just the Riemann hypothesis.
I mean, that's the whole. I think it's overkill, but
Okay,
it proves the point.
I think so too. But there is one statement. Look at all the paragraph for the proof of the Riemann hypothesis. The last paragraph is gone. That eliminates everything. Yes, it's a before, but we had to put discussion about it down below before. Now it just goes to because of lemma 4. Done. You know what I mean? So that's the reason. So that the final proof of the Riemann hypothesis is very short and sweet. And here it is. The proof of the Riemann hypothesis is like one page. After you have those simple conditions shown.
Lemmas.
Yeah. So each one of those lemmas presented a certain condition. I mean, upsilon in that form when the zeta function equals 0 is a condition that is required for the zeta function. And so here we go. So another condition is that the real parts, let me just read it. Actually, Greg, you read it. My mouth's dry. And
Proof of the Riemann hypothesis. Let rho sub h, that's a superscript, right?
Yeah.
Be a hypothetical non-trivial 0 off the critical line. Recall that equation 2, which is remind me what equation 2, don't go there, just
it's that identity.
Anyway,
it's identity.
Is necessary for all non-trivial zeros off. Is that the Riemann oscillator equation?
No, it's that real part plus real part equals 1, and the imaginary parts are equal.
Okay. Is necessary for all non-trivial zeros off the critical line to exist due to symmetric properties that follow from Riemann's functional equation. In order to prove that it is not mathematically possible for any non-trivial zeros to exist off the critical line, substitute rho h in for S in 23, and then in turn substitute that in for the real part summation in 2. Then do likewise for the second term with 1 minus rho h. This gives 1/2 plus that whole mess equals 1. So you get 2 terms of 1/2, and all the other things cancel out.
Yeah.
Okay, recall that in 2, that you call that J's, or
where
J sub rho h equals J sub 1 minus rho h.
Imaginary part. Imaginary part.
Oh, I'm sorry. Oh, that's an I. Okay, I knew. Okay.
Yeah, it's
imaginary part equals the imaginary part of the 1 minus the conjugate, and this implies 2 times the imaginary part plus I times that whole thing equals 0, and the factors 2 imaginary row of I plus I cannot be 0 as described in lemma 3. Therefore, the second factor must equal 0. I need more page here for the symmetric type 2 solutions to be non-empty. Can you move it up? Thank you. The explicit form of epsilon, is such that now I want to see the 2 equations. Okay, so can you move it down just a little bit so I can see 38 and 39? There we go. That's it. All right. So what? Now you went too far. Okay. All right. That's good. All right. So in other words, because the second what's inside the parentheses in 38. It is the part that has to be 0. Therefore, 39 is true. That's what this is saying, because let's just see, because we know, let's see, the 2's cancel, the row.
You'd have to look at the explicit form of upsilon, and you'll see that you know.
Yeah, the explicit form of upsilon is such that all that. Okay, that implies the relationship between the values of the 2 functions.
Yeah.
Yep. Okay, now move down, please, to 40. Okay, and there's the upsilon of rho h equals minus upsilon of 1 minus rho h bar. Okay, and so that has to be true. This condition is required because the 2 terms in the second factor only vanish when upsilon of rho h and upsilon of 1 minus rho h bar are equal in magnitude and have opposite signs. However, this condition was proven to imply real part 1/2 in lemma 4. Since all real part 1/2 arguments are prohibited by lemma 3 from also being in type 2 set, the set of solutions given by type 2 is empty. The following is the only logical conclusion to the set of type 2 zeros being empty. The negative solution for 23 is extraneous. While the type 2 planar solution of property 2 exists, as proven in lemma 3, it is not critically symmetric and therefore does not comply with property 1 as proven in lemma 4. Because 23 describes all zeros of the Riemann zeta function that do not have a real part 1/2 as proven in lemma 3, 23 contains only trivial zeros. Because all non-trivial zeros must comply with 2, no non-trivial zeros could exist as type 2 solutions. And because there are only 2 types of solutions for all zeta sub s equals 0, all the non-trivial zeros of the Riemann zeta function are restricted to the type 1 solution. Since the type 1 solution is on the critical line, all the non-trivial zeros rho n of the Riemann zeta function have a real part 1/2, and the Riemann hypothesis is correct. That's it. Well, that's pretty slick.
There's not much anything hidden, you know.
Pretty
it's
slick.
just kind of.
Yep. Yep. This thing, it's been written and rewritten a few times, so I know that.
Yeah, it is.
That
It has.
this is not the way I remember it, but this is actually better.
Yeah, we're just
So-
cutting out the fat.
Yep. It's very good. Very clean. So I don't know. Is anybody? I know we've been at this for well over 2 hours now. Is anybody in the chat had questions or comments?
Your guy dropped.
We've kind of gone all over the map. We attempted to do it with using the AI, and that didn't. That was struggling. Let's put it that way. So we went back to just looking at the paper itself.
Your British
So-
mathematician Greg dropped off the Zoom call. Maybe he just went to bed.
That's okay.
All
That's
right.
okay. But is there anybody in the YouTube chat that we can see their comments? Is anybody saying something that like a specific question?
Yeah, well, Mr. Shank said we may have to do another stream to put everything in the AI, but we may not. I know that was kind of a while back. Do you still?
That was a while back.
We don't mind doing
Yeah.
another stream. I could do this again, and we could put up.
Yeah, I mean, it feels like we were kind of all over the map, and we spent a lot more time.
Yeah.
We wasted a lot of time. It felt like.
He
But,
said he
you know-
said it's a good stream, and then there's another mathematician from Nepal. Gabriel is just listening. Hi, Gabriel. There was a I don't know, some mathematician from Nepal says that the Riemann hypothesis is simple, but people make it complex. Okay. So, does anyone have any questions? Because I think we got to end it. We could do another stream. Let's do that, because I know this is Zoom call. Part of this is going to cut off, I think.
Yeah.
Which we'll still stream, but I think you'll be good. So it's been 2.5 hours. We can wrap it up. But I guess I'm happy to answer any questions if anyone in the chat. We can do this again. But it would be really good to have some mathematicians come and challenge it. But maybe we can do another stream in the future. We'll get that. Yeah, let's get that.
We're looking for.
Yeah, go
We're
ahead.
looking for challenges. We're looking for people to find a hole in it, and is it done? Is something get missed? I've gone over this myself, not as much as Jeff, but I've gone over it many times, and it's changed. It's evolved quite a bit over the years, but this is the best form that I've seen so far, and I don't think there's much missing, and the more I look at it, the happier I get with it. So
yeah, me too. No, I don't.
We
I
just
think
need-
there's. I kind of have like what you have. The issue is where you found all this research and you want to include it all in the paper. You do that too, right? So I found all this cool
there's a
stuff,
ton
and I'm
of-
like, oh,
there's a
this
ton
is
of
what I
things
was
we could
doing here.
include.
This is what I was doing here, and I want to show because it's like that's part of the research behind it.
yeah, I
So
get
that's
it.
why
I
there's
get
a
it.
lot
Well,
of the
we get it, but this is
as a proof. We want something that's short, simple, and I think this is the shortest and simple it's ever been. Yeah, that's why I put the separate thing up the other day. I sent you guys, and it's 9 pages long, so anyone can zip through it. There, it's what
I remember the
calculus
first
and all-
version was like 70 pages,
Well, that was a different proof. That was a different proof.
Yeah.
So I
And then
discovered.
we
Yeah.
whittled it down to 6 at one point, and then you had
Yeah.
to add stuff because there was
Yeah,
a
the
few
seven.
details that weren't
That was
included.
like 15 years ago. That one. That was a long time ago.
Yeah.
The
Well, I remember messing around with it, a couple of years ago, and
yeah,
it's definitely different than it was.
This is
then.
no, yeah, this form, this result, putting it in the form of the oscillator and solving directly, it was 2 years and 3 months ago. I think we put the first video up. I think I was talking to you.
Yeah.
I don't know. I was talking to you for about a year before we put this up, and then we got Danny on.
Like 3 years ago, we were working on this.
Yeah.
And we did. Anyway, well, so I just like to put in my 2 cents, Jeff, and that is to say, first of all, it's probably obvious that Jeff has done most of the work. He's put my name on it and Danny's name on it, and I appreciate that. And I've definitely had some input into making this thing happen, but Jeff's done the lion's share of the work. So just to be clear on that. And second thing is, we love math. We do this for the love of it, but it would be nice to be able to say, hey, I think we've done it. I think, we found something that actually, satisfies the conditions. It should be a big deal. And yet it's a real difficulty, as Jeff said earlier, to get somebody who has the bona fides, who has the credentials that we need to be able to get enough of a critical mass of serious people to take a look at this and say, yeah, there's something here, and at some point, I guess we'll get enough, well-respected mathematicians to say, yeah, they've done it. That's what we need, because at this point, I don't know what more we can do. We can continue to, work on the paper and try to make it more clear or make it shorter. It's hard to imagine making it much shorter. And that's what we're looking for. We need that. We're just regular guys. None of us are academics. We've said that already, but we are mathematicians. So we can hold our own with anybody, I think, as far as that goes. So if you have a means to do that, help us out. We're trying to bring something to the world that we think is a good thing.
There is one thing. Well,
that's my 2 cents.
Yeah, that's good. So first of all, Greg and Denny have been an incredible amount of help, and it actually is not possible without them. There are a lot of things that were laid out in the beginning that just didn't make any statement that was correct. I had research that showed that a proof is possible when I brought it to these guys. So they did help put in a form that actually proves it. So that's reality. I brought the research and the three of us put it together. Second of all, what we could use is a next step. Obviously, it would be ideal that a mathematician would defend this paper and proof. But if not, the very least, what we could get is somebody who is on archive. We could upload it there. People will tear it apart there. So if we could upload it there, but we have to have permission. We need somebody to vouch for the paper. They don't need to vouch to say it's correct. They just need to say it's worthy of upload. And then we can get in, upload it. That would be good. I don't really have interest in hunting down math journals at this point. I think it would be better just to have a mathematician or two just step forward and say, this is right. That would be ideal. And I think they could do that in archive, So if we get somebody to vouch for the paper, the word
peer review.
They don't even need to peer review it. To vouch for somebody to upload to archive is just to keep the junk out. That's all. They just don't want, this is not a junk proof. It's a good proof. So if they could just say, hey, this is maybe where the discussion. I haven't had time to look at it all the way through, but this paper, is decent. And then we upload it, and then there's lots of mathematicians who would love to beat it up. That's where I think some interesting. That might be the next step too. So, all right, Denny, any thoughts before we close?
Well, again, I'd like to point out that the big problem in getting mathematicians that are somebody to go for this is that the algebraic geometers, especially under Grothendieck, Alexander Grothendieck, who's now dead, of course, but he convinced everybody that only algebraic geometry would prove the Riemann hypothesis. It would never be done by just complex analysis like you've done. And the proof would be horrendous. It would be sort of like classifying all the finite simple groups, which has been going on for a long, long time. And it's a huge literature. And so the problem is a sort of a psychological one. When I was a student at UC Berkeley, undergraduate, I had an advisor by the name of Professor Maxwell Rosenlich, who won the Cole Prize by showing that the idea of a Jacobian in integration and calculus could be, which is key for integration, could be generalized to algebraic geometry. So his paper was on generalized Jacobians. And he won the Cole Prize for this, which is a very important prize in the mathematics. And then his students, especially Brownstein, Bronstein, went to work at IBM Yorktown Heights Research Center. And they pushed Rosenlich's ideas until it used to be that if you had some calculus and so on, and you were writing a program, you got a dump because it didn't quite work out. There'd be like 50 or 30 or 50 pages of stuff that no one could know what it meant or anything. It turned out that this was largely Bronstein's idea of using algebraic geometry and generalized Jacobians to give algebraic symbolic solutions to various integrals. But no one knew, that I knew of anyway, including myself, knew just how to use all this output. So it finally stopped. But he wrote a book published by IBM, Yorktown, called Symbolic Integration I, or where the capital I stands apparently for Roman numeral 1. And it explains how he all this algebraic geometry allowed integration to be done symbolically rather than numerically, using algebraic geometry. And no one could use that I knew of. But of course, maybe I didn't know the right person. I've been living in Spring Lake, Michigan, which is basically Podunk, Michigan, for like since '72 or something like that. And so I wouldn't know if there were some people at IBM Yorktown Heights or somewhere who knew how to use all this extra information in the dumps to an advantage, to help him calculate various difficult integrals. And so it may be that this work hasn't fallen by the wayside. I don't really know. But if you're interested in pursuing this, the book is Symbolic Integration I, capital I, by Bronstein, Bronstein.
And Denny, the point, how does that relate to this? Just
because mathematicians feel nowadays that algebraic geometry is the only way to go on this Riemann hypothesis.
I see.
Denny has long believed that.
That's a big.
And this would mean Bronstein's work in his book, Symbolic Integration 1. And So,
So you're saying this would prove that his ideas maybe were valuable or weren't,
well, his
were wrong?
ideas may have been valuable, but no one
I
knew
see.
how to use them that I knew of anyway.
I see.
So they fell by the wayside, although there may be some people who do know how to use them and they can turn them on by, somehow in their
And so,
program.
so
And so if they
that
get
would make this more valuable somehow? That's what I'm missing. I'm still trying to get the
say it
connection.
again, Greg, I didn't catch that.
Sorry.
Well, let me
Did I
let me
say-
summarize because we got a question from the chat. Let me summarize what Denny's saying, Greg. Denny has been long held that there's nobody is going to. Mathematicians are all in the school of algebraic geometry. They only believe
Right.
that the Riemann hypothesis is going to be proven by algebraic geometry. And if we present a proof, and he has gotten some people emailing back suggesting this way that if this is a simple proof of the Riemann hypothesis, then it must be garbage. End of story. He doesn't believe they even will look at it, so it's that far you're removed from their mind that it just couldn't be true. So even with this, somebody's going to have to spend a little time to understand it. But at that point, that's where he's going with that. Hey, I got a question from Gabriel. I was kind of talking with him in chat, but let me just kind of ask. What's the latest number of reads, Greg, at ResearchGate?
What's
Latest number of reads of this
number of
paper?
reads? It was like 9,800 last I looked.
Almost 10,000 reads. So Gabriel
quite,
says
yeah.
last time he saw it, it was 3,000 plus reads, and he says it seems there's enough eyes on the paper from his perspective. Do you think the paper could use more attention? That's why I was kind of mentioning archive, you know what I mean? There's mathematicians there. And he's saying, I'm wondering what it will take to get an audience with a credible and well-known mathematician. What that would take, to get a mathematician. I don't know, Gabriel. We don't know. I think time, it's just going to have to be some mathematician that watches maybe these videos and goes, I want to look into it, and then they read it. And like I said, the one mathematician who didn't show up, one of them that didn't show up, there's a number that didn't, but he let me know. He let us know he likes the research. He likes what we're doing. Just I don't know. Yeah, there's at the beginning of this video, there's some reasons they might have to not publicly defend it or acknowledge the paper. Yeah, because what happens if an error is found? Then they look like a fool because it was simple proof and they missed an obvious error in a very simple proof. That's not good.
Yeah.
But I think there's got to be some point where people go, well, if there's a problem, then there should be a way to check for it. Right? So if there's a problem, if these mathematicians, are very bright, they should be able to look at a paper and say, yes, the problem is here. Yes, the problem is there. The proof is not satisfied by this. And if silence after a while does start to mean it's right, because, to my opinion, silence long enough, if enough people have read it, and enough have, it's, at one point it's got to, I think maybe another mathematician might one day say, look, nobody's coming out and saying, I'm going to do it. And they might. Maybe a guy who's retired, really cool, kooky, good guy. He might, say, I'm going to do it. I'm going to defend it. And I'd like to see that. But I don't know the future. Originally, when I went to Greg and Denny, it was kind of like, I think I got something here, but I can't go any further. I don't see a problem in it, and so that's where it started, and that's kind of why we're putting it out there. Is we do want to know also. Do you find a problem in this? Let us know.
And I would take it a step further and say, if you read the paper, if you take a serious effort of looking at the paper and you say, hey, I think it'd be clearer if you did X or Y. Again, that's not necessarily a credit, finding a problem with the proof, but you might say, hey, it could be more clear or more acceptable if you did X.
Oh, yeah.
And we're very open to that. We've been through a lot of revisions already.
Mm-hmm.
So if you want to do that, we're very open.
Yes. All right. Well, I like this. This is fun. I think we're at 3 hours though. So
Yeah, it's a long time.
yeah. So let's do that. All right, we're doing it again. We're doing it a shorter way next time. We're gonna prepare everything ahead of time. Greg, I'll send you a copy of the Word document of the short version. I sent you the PDF, but I didn't send you the Word document. That way you can kind of just copy and paste it. We'll see how fast we can copy and paste in there to make it, get all the information.
Yeah, and I would even
in an hour.
It might be good to start, Jeff. I was thinking it might be good.
Well, yeah. All right. So you can do. Have you been to this site yet?
Yeah, I will. I will. I was thinking I could
can
have everything all ready to go and just plug.
Just know you're gonna have to do. We're gonna have to do
and
it
then
again.
we know ahead of time it's not going to be a problem.
Yeah.
I don't know. That might be a good idea.
I think that's the thing is we get as much, get everything ready so we can just copy and paste it. We don't need to have all the text, but just the lemma and the proof that text.
No, but I'll just literally have my conversation all ready to go, and all I have to do is plop them in there. And I just did it that morning, so I know it's going to work. The AI doesn't change that much.
Yeah. No,
something like that. So we can just have a real effective and smooth.
Yeah. The best way is to do this at like 5 o'clock or 6 o'clock, and then stream at 8 o'clock, and it's just continuing it right from there. After all the information's in, just plug the information right before we live stream. No, but then they wouldn't see.
Yeah, that was my thought.
Yeah, but then
we could start clean, and that might be as convincing as anything.
I think.
If somebody has a question, yeah, I think so.
All right, so here's what we'll do. We'll discuss it.
I'll be happy to do that.
We got it. This is what we'll do. That's right. We'll talk about it. Plan the format. Next time we stream, I'll give some notice. Whatever. Next time we stream, we'll kind of let everyone know.
How about a week from tonight?
Yeah. I think I'm good, but
same time.
I think I'm good. If not this week,
we won't go as long.
Right. I think we could have everything in there in a half hour if it's all prepared, and the next hour it could be hour and a half could be just going ahead and doing it. I like that. Maybe we can give the mathematicians maybe some of them because the holidays. I didn't give them enough notice. I didn't give them enough notice, so I could probably send another one. Say here, that way they have time to look over the paper. Because maybe they didn't feel confident, they didn't look over, have time to look over it long enough. That's why
we could say 2 weeks from tonight. How about that? I don't know.
I think what I'll do is I'll kind of write some other mathematicians, maybe give feedback. A week or 2 weeks, one of the two. We'll figure it out. We don't need to decide now, but let's plan on.
Okay.
We're gonna do it again.
All right. I'll do my part.
All right, and I'll do mine. Sound good, Denny?
Sounds good.
All right.
Okay.
All right. Good.
All right. Well, God bless everybody.